Dear students, welcome back. So this is the 8th assignment of this course and the first assignment in ODE. As it is already indicated in the first course handout and otherwise, please note that the assignment problems to be discussed in the live sessions are not meant to be done by the tutors line by line for all the problems. They cannot do it in the duration that is given. So ideally they will do some prototype problem which they find is difficult or you cannot do. So it's always better you attempt these problems before the live sessions, have your questions and doubts prepared, and go with those questions and doubts to the tutorial session so that the tutors can help you out. It's also better to discuss with your friends who were able to solve the problem so that you all go with only those questions and doubts which no one was able to solve, right? And in this way you can also use the tutorial session to discuss questions and doubts related to lectures with the tutors and so on, and so it need not be restricted to the problems given in the assignment sheet. Okay, so from the ODE part we're going to have a slight variation of whatever system that you have been following up to now. So in the ODE part you are going to have two types of problems. One is the assignment problems to be discussed with tutors in live session, okay, whatever we say here, okay, and then you will have another set which will be given by me in a video recording, which is this session, okay. So the assignment sheet will contain two parts. So the first part will be discussed in the live sessions and the second part will not be discussed in the live session. I will provide hints here in a video recording, right? And you can of course kind of ask questions related to this to tutors as well. They should be able to sort it out or kind of help you out in case it's not clear in these video recordings, okay. So that's the summary. So this is how we will do the OD part of the course. So let's start with the first problem in the video recording, which is the sixth problem of the assignment, okay. So what is this 6a? 6a is asking us to show that this yc is a solution to the differential. It's a solution to the yc solution to this differential equation y prime y square equal to 0, okay. So you have a one parameter family of solution and we need to show that this solves this differential equation. So basically, and this is a non-linear ODE, okay. So we just have to verify that this is satisfying this differential equation. So let's differentiate yc. So if you differentiate it, you will see that it's 1 minus 1 x plus 1 whole square. So what is yc prime plus yc square? Yc prime is minus 1 x plus 1 whole square and yc square is x plus c whole square. That's 0. So it satisfies the differential equation, right? Okay, so when can this be a solution, right? This is solution when x is not equal to minus c, right? So for right, when you, so this yc is a solution when x is not equal to minus c. So in your, so your domain I, so if you have if this ODE is given in an interval I of R, this I should, so this I intersection this minus C should be empty, right? basically minus c should not be sitting in the domain, or should not be included in the domain of this function, okay, of this. So the solution is valid in an interval which does not contain minus c. This is true for each c. So as you change c, the domain has to change, right? I mean, so in general this is a one parameter family of solution. So that's why certain subsets of R depending on C. Okay, now let's do y 6b. 6b is asking us to find a particular solution and the interval on which the particular solution is valid, corresponding to the initial condition. So let's take this initial condition y0 equal to f, right? So the OD is not changing. OD is this, right? OD has not changed. What we are giving is an additional information, which is the initial condition. So now it becomes an IVP. So using this initial condition, what you can do is that you can, and if this is the one parameter family of solution, so you can actually compute the C. So if yx is 1x plus c is the general solution, then what is given is y of 0. So y of 0 will be 1 over c, but y of 0 is 5. So 5 is 1 over c, which implies c is 1 over 5, which means your particular solution is 1 over 5. So 5x plus 1, 5 by 5x plus 1. Okay, and when is this valid? So this solution, this particular solution, is it valid for all x in R? No, right? The answer is no. It is valid for x not equal to minus 1 over 5. So what can be your domain I of the thing? It should not include minus 1 over 5. But then minus 1 over 5 means you have two possibilities, that is minus infinity to minus 1 over 5 and minus 1 over 5 to infinity, right? So this I could be subset of this or this, right? But then can it be subset of any of these? The answer is no, because the initial point is given to be 0. So the domain should include the initial point, and in this case this 0 is included in this interval, right? Which means your I should be a subset of minus 1 over 5 comma infinity. It cannot be a subset of here. So now so this is B1, right? Now let's do B2. B2. So B2 is given to be y2 is equal to minus 1 over 5. We do the same thing. So y of 2 is 1 over 2 plus c, which means y of 2 is minus 1 over 5, 1 over 2 plus c, which tells you that c is minus 7. So again, the solution is valid whenever x is not equal to, right, whenever x is not equal to c is minus 7. So okay, let's write down the solution. So the solution is yx 1 over x minus c, and this is valid whenever x is not equal to 7, right? So the possible so the possible intervals are minus infinity to 7 and 7 to infinity. So I can be a subset only in that interval on to which the initial point 2 belongs. 2 belongs to minus infinity to 7. So this is for this initial value problem, the solution is valid for any subset of minus infinity 7. Okay, so the purpose of this problem or assignment is, as you can see, you have a one parameter family of solution for this ODE, and depending on different initial condition, right, for the same OD. So the OD does not change, but if the initial condition changes, the domain in which the solution exists can also change, right? That's what we have seen here. Okay, now let's look at problem number 7, which is analyze the existence and uniqueness of this initial value problem. So what is the purpose here? So here you see the OD is given, which is this, and the initial condition is given, but initial condition, the value of x0 and y0 is not given. It's some generic, right? It's a generic value, x0 and y0, or some elements from R, right? It's not given. So when you say analyze the existence of and uniqueness of this problem, basically one has to conclude for what values of x0 and y0 will this initial value problem admit a solution and not admit a solution, and if it admits, how many solutions, and so on. That's what analyze the existence and uniqueness mean here. So again, so you see here the OD is fixed. If you change x0 and y0, that means the initial condition is changing, and depending on that, the existence and uniqueness of solution can change. Okay, so let's do step by step. So first, the case 1. Okay, in the case 1, so first of all, you notice if you have to worry about existence uniqueness, you have to write it in the Picard's theorem form hypothesis, and you see that your f of xy is precisely in this form, right? So this is your f x y. That's so x. Okay, this is your f x y. Okay, so now so what should we verify? We should verify what is whether fxy is fxy, and for existence we should verify the continuity of fxy at every point or around the neighborhood of the initial point x0 y0, and the partial derivative. So basically what happens at these points, right, x0 y0. So you can very well see f of xy is this quantity, f of xy is this quantity, right? This is f of xy. So what can be your so is this is this defined everywhere? The answer is no, because when the denominator is 0, that is when x0 is 0 or x0 is 2, then f is approaching infinity, f is blowing up, right? So this is not so at 0 and 2, so except at, so whenever x is, or whenever you, let's say x0, whenever x0 is not equal to 0 or x0 is not equal to 2, right? Whenever x0 is not equal to 0 and x0 not equal to 2, by Picard's theorem, there is a unique solution to this ODE. There is a unique solution y by Picard's theorem, right? In a neighborhood, in a neighborhood of x0 y0. In other words, in a neighborhood of x0. So there is a interval around x0 in which there is a unique solution, as long as this x0 is not equal to 0 and not equal. So case 1 is precisely the case when x0 is not equal to 0 and x0 is not equal to 2. Y0 could be anything, that doesn't matter, right? Y0 did not play any role here, right? So that is case 1. So in this case, you have unique solution. Whenever your initial point is different from 0 and 2, you have a unique solution by Picard's theorem in a neighborhood of x0. Now what is case 2, the second situation, right? The second situation, so you see this ODE that is given to you is a linear homogeneous ODE, That's the type of this ODE, right? It's a linear homogeneous ODE. So it's already of this form, as you can see here. So we can actually write it in this form: y prime y equal to 2x minus 1 x minus 2, right? Then you can integrate them, right? It's in this separable form also, right? It's also a separable ODE, right? It's in the separable form also. So what you get is log of mod y, okay, times this is log of precisely x square minus 2x, okay, plus some constant. Let's write it as log of c. So that's going to give you a solution which is y of x is equal to c times x minus c times x of x minus 2, okay. Okay, so that's your general solution, right? That's the one parameter family of solution for this first order ODE that is given to us, okay. So now the second situation case is if your initial value is x naught and y, because case 1 dealt with when x naught and so when the initial point x naught is different from 0 and 2. So in case 2, let's say x naught is equal to 0 or x naught is equal to 2. Maybe this is not visible. Let's write it with. So x naught is equal to 0 or x naught is equal to 2. So in this situation, what happens? You can see here, if x naught is different from, if x naught is, so what you get is that y of x naught, if x naught is the initial condition, it's c of x naught minus 2, y of x naught is given as y naught, right? And if your x naught is 0 or 2, this is 0, right? So which means that if you choose x naught 0, x naught or x naught 2 and y naught not equal to 0, that is case 2. So this is your case 2. If you choose y naught not equal to 0, then there is no solution, because when x naught and x naught is 0 or 2, the right hand side is 0, which means that y naught should always be 0. But if your choice of y naught, which is something given in the beginning, right, to begin with, if that is non-zero, then this cannot be a solution for any choice of c, doesn't matter, right? So there is no solution. So for this situation, there is no solution, case 2, when x naught is 0 or 2 and y naught is a non-zero quantity. So third situation is when x naught is 0 or 2 and y naught is also 0, okay. In that case what happens? You have infinite number of solutions, because we have already seen yx is c x minus 2, and this initial condition is always satisfied, but that is satisfied for every possible c in R. So you have infinite number of solutions, right? So just to, this is the third situation, okay. So just to summarize, what is the purpose of this problem? This problem is telling you, you see the OD has not changed, right? the OD is same, but the initial condition can the initial condition can change the nature of solution. Depending on the initial condition, the same ODE can have a unique solution, can have no solution, and then can have infinitely many solutions. Okay. Okay. So now let's go to problem number 8. Is there anything else I want to say? No, it's fine, right? Okay. Okay. So yeah. So now let's go to problem number 8. What is problem number 8? Now problem number 8 is telling us that you are given an interval I, which is the domain, open interval, and you are given a continuous function Q, right? So 8a is asking you to check or show that the constant function 0 is a solution to the given ODE. Okay, so this is a linear homogeneous ODE, right? So it's a linear homogeneous ODE which is given to you, which is y prime qx y equal to 0, and what we need to verify is 0. That's easy to check. If you take the constant function, then you know that 0 prime is 0 plus q times 0, and that's 0. So the constant function is a solution to this ODE. So this is 8a settled. Okay. So we have already seen what is linear homogeneous, right? I don't have to recall. So here the right hand side, so there is no function independent of y variable, and it's linear because it's linear in the y variable here, right? All this is something which you can check and verify. We have seen lots of examples regarding that. So the constant function is a solution to this problem. Okay, so the constant function is a solution to this problem. Now let's do B. What is B? B is saying if U is a solution of the given ODE, so this ODE is the same ODE, what we have written here. If U is a solution of this given ODE such that it vanishes at some point x0, right? So let's say I is this interval. I is this interval on which the ODE is prescribed, right? And there is a point x0, right? So this is asking you to show that if U is a solution which vanishes at some point x0 of the domain, then U has to be the constant function 0. Okay, what is this saying is that this is saying that if you have if you have a solution to this problem which vanishes at a point, then it has to be the constant function 0. In other words, you cannot have a solution. Suppose you draw the and suppose let's say this is the interval I that we are working in, right? Then what is the saying that you cannot have a solution like this, something that passes through like this, or something that goes like this, or something that goes like this, and so on, whatever, right? Basically these are all different. So you cannot have solutions like this. That's what this statement B is telling you, that if it vanishes at one point, then the function itself should vanish everywhere. It cannot vanish at one point and can be non-zero at that point. That's not possible for a solution of this ODE. Okay, so let's prove that. So let's start with the initial. So let's take y prime q y prime q of x y equal to 0 with y of, let's take the initial condition, because x naught is given to us. On this x naught, you take this initial value problem where you prescribe at x naught solution 0. What is given to you is u is a solution to this IVP, right? U solves this IVP, okay? But you also have the constant function 0 also solves this IVP. You already have two solutions to this IVP, right, as per the given thing. But Picard's theorem, let's verify the hypothesis of Picard's theorem, which talks about the existence and uniqueness. And for that, so in this case, what is your f? Your f of xy is minus qx y for the linear homogeneous case. So what is the y derivative of f? It is precisely minus q, right? It's precisely minus q, and q is given to be continuous, and f is also continuous, right? And there is no issue in the domain I, right? So they satisfy the hypothesis of the Picard's theorem, and that Picard's theorem tells you then the solution has to be unique, right? Which means these two solutions has to be the same solution. They cannot be different solution, which means u has to be the constant function 0, right? So that's how we rule out the situation that the solutions of the linear homogeneous ODE cannot be of forms like this where they become 0 exact, at some point and non-zero at other points. That's not possible. You cannot have such solutions for linear homogeneous ODE. So that's the beauty of these theorems, right? See, here we didn't even solve the problem. We didn't even write down the formula for the problem, for the differential equation, but still we were able to conclude some property of the solution, right? So this is what is called the analytical approach to the problem, where we actually we use some information to conclude about the solution without exactly knowing, without knowing the exact formula of the solution. Okay, and this is very important in various situations, because you will not always be able to write formulas for solutions. So this kind of approach is very important in mathematics, and that's the beauty of this thing. Anyway, now let's look at problem number C. Okay, so C is a statement where you are given two solutions u and v, and they both coincide at a point x naught. Then they should coincide everywhere. It's very similar to the previous case B, where instead of 0, now you have some v. So if you take v to be 0, v to be the constant function 0, then then C reduces to B. So C is more or less a generalization of B. So is that true? The same argument like B will be valid. So basically, if you have two solutions and if they coincide at one point, then they should coincide everywhere. That is the statement of the result that we need to prove. So you are given u and v, both are solutions, and they are such that u and v coincide at x naught. What we do is that we define a new function, let's say w, which is u minus v, right? Now what happens to w is, since u and v are solution of that ODE y prime qxy, since u and v are solution to that, w is also a solution to this ODE, right? Because of the linearity of this, ODE, right? You can verify that quickly. You can just substitute this. You can see that u prime plus qu will vanish, v prime plus qv will vanish. So therefore w prime plus Qxw will vanish. Okay. Okay. So now we also have, from this fact, we have W of x naught to be 0. So W is a solution to the linear homogeneous ODE, and W vanishes at some point. So from the previous problem B, we know that W should be the constant function 0, and if W is the constant function 0, which means U should coincide with V. Right? Okay, now there is one more, right? Problem. There are two more. Okay, D and E. Okay, we need more space. Let's continue on later, and then we will come back. Let's see if I can continue it here, right? Let's see if I continue it here. So let's do problem number D. Okay, what is D saying? D is asking us, show that the set of all solutions of the given ODE form a vector space over R. In other words, suppose you define the set S to be the set of all functions y such that y prime qx y equal to 0. This is in the given interval I, let's say. Okay, if they are 0, so in that case you can even bring the I dependence in the definition. So let's call the set as Si, suppose, right? So Si is the set. So what is this D is asking is, it's asking us to show that this Si is a vector space. It's a vector space over the real field, the real numbers. Okay. Now, how do we prove that? So what should we prove to prove vector space? You know the definition of vector space, right? First of all, we have already seen in 8a here that 0 is a solution, which means 0 always belongs to Si. So the 0 function belongs to Si because that's a solution to that problem, right? So Si is non-empty, at least that we know it's non-empty. So it's non-empty. So Si is non-empty. Okay. And if there are two solutions U and V of Si, then for any alpha beta, let's say in real number, if you look at alpha U plus beta V, and if we show that this is also in Si, then we have shown that it's a vector space over R. Right? How will that happen? So to verify whether this happens, what we need to check is that this is a solution to this problem. But that's precisely what linearity of that problem means, right? So if you actually compute alpha U plus beta V prime plus Q X alpha U plus beta V, if you compute this, so use the linearity, right? You can separate them out. It will come out as alpha U prime plus alpha QU, similarly beta V prime plus beta QV, and each of them is individually 0. What's happening? I'm touching somewhere. Okay, each of them is individually 0. So this is 0, alpha times 0 plus beta times 0, which is 0. Okay, so that's what what we need to prove, that it's a vector space over R, and that's what we have done. It's a vector space over R. Now there's a further question there. Can a similar conclusion be made for any kth order linear homogeneous ODE? Right? So basically you are saying, see, this is a first order. See, this is a first order ODE, right? This is a first order ODE. If I replace with a kth order linear homogeneous ODE, so this is a first order linear homogeneous, and if I replace this question with a kth order linear homogeneous ODE, is the statement that the set of all solutions is a vector space over R is still valid. Okay, and the answer is yes. Why it's yes? What in this entire proof of D that we did here, where did we use the order of the differential equation? Only for differentiating, right? So the property that was used to prove that Si is a vector space was one, of course, that 0 belongs to that, to the solution set, which will be true. And second is the linearity of the equation of this ODE. And even if you take kth order, the linearity property is still valid. What you just need to do is you have to differentiate k times to really check this, whether it satisfies this equation or not. So the answer is yes. So please go ahead and do it if you. So let me. I don't know. Okay, I thought I was getting some extra space. Okay, let me maybe I will erase this diagram here. I don't know what I usually get extra space. Something's missing. Okay, it's fine, it's okay. So we don't need, I will erase just this diagram. Okay, so okay, so now we have verified the D part. Now let's do E part. Since we have shown in the D part that the solution set Si is a vector space, E is asking what is the dimension of this vector space. Okay, what is the dimension of this vector space? So let's find that out. So for that, let's look at this. So it's E, right? If you look at this problem ODE, you can write it as y prime over y is equal to minus q, and if you integrate both sides, what you will get is yx is equal to exponential of integral of minus q, right, with some constant, say c. So let's write it properly. So what you will get is y of x is c times exponential of minus integral q. This will be actually, this is usually done from the initial point. If you have whatever, that doesn't matter, whatever point you want to start with, is qs ds. Okay, now so this is some function of x. So what you have written is that the solution of that ODE is c times v. So this is the one parameter family of solution where this v is given in terms of q, which is a known function, right? So your general solution is this. What this means is that any solution to this ODE that you have here is a scalar multiple of some function, which means which means y is in SI, and any y in SI is of this form. It's a scalar multiple of some function, which means SI is one dimension. Right? So here the one dimension depends on the order of this ODE. So because this was a first order differential equation, the dimension is 1. In fact, this result is true for a linear homogeneous. If you take kth order linear homogeneous, the dimension of the solution space will be k. Okay, that is something you will see later in the course. Anyway, so we have at least proved it for the first order situation. Okay, so what is the summary of this problem? If you understand, if you have a linear homogeneous ODE, more or less we have classified everything about the solution set, right? One, we have a formula for the solution. When we did E, we actually obtained a formula for the solution just by integrating, because it was a separable type ODE. So we have a formula for the equation. Second, we said, and as you can see from the general solution, so it's a one parameter family of solution. All these solutions, though they are infinite number of solutions, because it depends on C, and C is from real line. So you have as many solutions as real numbers, but that if you count as the number of solutions. Whereas if you see it as a vector space, it is of dimension 1. Right? And then we have also observed that you cannot have solutions which are vanishing at a point and not vanishing at other points for a linear homogeneous ODE. The linear homogeneous ODE, if it's vanishing, then it's vanishing everywhere, otherwise the function is not vanishing anywhere. Right? In fact, that you can actually also see from this formula here. It's exponential of something. Okay? So that's the purpose of, so in problem number 8, we have more or less classified the solution of linear homogeneous ODE. Okay, now let's move to problem number 9. So this is the Picard's iterative process. What is strange is why am I not getting these extraction? Maybe if I don't know. Let's see. Anyway, so problem number 9, we are given this initial value problem, okay, and we have to find its solution by using Picard's iterative process. So let's start by the iterative process. So what is your fxy? It's the right hand side that is given, which is 2 by 3 y power half, right? That's your fxy. And what is your initial point? X naught is 0, and what is your initial value, which is y naught, which is also 0. Now what is the Picard's iterative process telling you? You start with a function which coincides with the initial value, right? At the point x naught. So we said we will always choose the simplest one. So let's choose the zero order approximation as a constant function 0. So that satisfies this initial condition. So u0 of 0 is 0. So it satisfies that initial condition. So that's the first function that you take, and then you use this Picard's iteration thing where you the recursive formula, right? So you take uk is defined, in this case it will be defined as 2 by 3 integral of fx something. In this case fx is 2 by 3 square root of thing, so uk minus 1 square root of that s ds. Okay, this is the iterative process that we will be this is the iterative formula, the recursive formula that we will be using, right? Okay, so now using that, if you compute u1 of x, if you see, is 2 by 3 0 to x, it's 0 ds which is going to be 0, and so on. If you actually see, uk is 0 for all k bigger than or equal to 0. Right? It's a constant function 0. So this is a constant sequence which will converge to 0. So your solution is the constant function 0. Right? So you can verify it immediately here that so the constant function 0 is already a solution to this, and this is a nonlinear problem. Okay, and this is a nonlinear problem. There's a y, square root of y. Okay, so the constant function 0 is a solution, and we have obtained this from the Picard's process, Picard's iterative process. Now let's go ahead, and so the purpose of this exercise is much more than that. So in the lectures we had mentioned that the natural choice is to choose the constant function 0 whenever your initial condition is 0 as the zeroth order approximation, like the way we did here. We chose u0 to be 0 precisely to ensure that this happens, that is, it satisfies the initial condition. The question is, suppose we don't do that. So for instance, in this case, if I don't choose a function which satisfies this initial condition, so if one chooses the constant function 1, for instance, that will not satisfy this initial condition, right, as the zeroth order. So if we choose your u0 to be 1, then what happens? Will it lead to a solution to the initial value problem? If yes, why, and if not, why not? Justify your conclusion. That's what. So if I choose, first of all, can we do this? Right. So that's what this problem is asking. Can we do this? Now, before we give the process using 1, let's just say that it doesn't really matter, right? So see, in the Picard's iterative process, how do you obtain the solution? You obtain the solution as the limit of some sequence that you construct. Right? And how do you construct this sequence uk? The sequence is uk, and so all these elements, so the sequence uk is constructed from kind of ensuring that in each process so the uk is actually solving the initial value problem where the data is given by the previous element of the sequence, right? So it's like kind of what do you call, bootstrap kind of argument, right? So you start with a u0, you plug u0 as a data, you get a u1. And how do you get that u1? You get that u1 by solving the initial value problem. So once you solve the initial value problem, automatically you are imposing that the initial condition is satisfied. That is how you are starting. So the only free choice that you ever had was the first function that you choose, right? Once you choose your first function, and if you use this process, then the second function will automatically satisfy the initial condition, which means in a sequence, only the first term is not satisfying the initial condition, rest everything. And you know in a sequence, if the first finite number of things, even if they don't have that some property, then, and if the tail of the sequence is respecting that, it's okay. Right? So in fact, I can start the sequence by throwing away the finite number of terms which do not agree with what we want, right? So which is why it doesn't matter. So that is the justification which I have given you before. What is the justification why it works? So it actually doesn't matter if I start with u0 equal to 1, which does not satisfy this initial condition, because u0 of 0 is actually 1. But that doesn't matter, because when you go ahead and find your u1, which is actually by solving, so what is this, how is u1 found? U1 is, of course, this iterative process, if you remember from the lectures, is coming from that ODE, right? This is coming from the ODE, where u1 prime is equal to, you write 2 by 3 u0 half, and then u1 of 0 is equal to 0. this is the IVP that you solve to obtain U1. Similarly, you for U2, so if you want to say UK, then you have to just do UK minus 1. That is how you obtain the thing. So except the first one, every other choice in the sequence will satisfy the initial condition. So that's not a problem. So if we start with 1, let's see what happens, right? So let's find U1. Okay, if you use the U1 to solve this problem, which is same as using this recursive relation, this integral here. So U1, if you notice, is 2 by 3, 0 to x. UK minus 1 was UK minus 1 is 1, of course, yeah. So square root of 1, so it's ds. So this is 2 by 3 s 0x, which is 2 by 3 of x, right? So that's your U1. Now if you go ahead and you find your U2, it is 2 by 3, 0 to x, right? 2 by 3 of s power half ds, which is 2 by 3, 0 to x whole power 3 by 2, which is s power half ds, which is 2 by 3, 3 by 2, s 3 by 2, 0 to x, and then divided by 3 by 2, which is 2 by 3, which is plus 1, right? So that's going to give you 2 by 3, 5 by 2, x power 3 by 2. So you can keep going on like this, right? If you keep going on like this, finally you will notice, I'm not going to do, I'm going to let you check for it yourself. So if you keep going on, you are going to see that UK is some AK x power BK, right? Because here is a 2 by 3 x power. So U1 was x power 1, U2 was x power 3 by 2 with some scalar multiplied. So there is some scalar multiplied. So UK is of this form, where as you have seen, your A1 is 2 by 3, your A2 is 2 by 3, 5 by 2, right? If you keep going on, you will get that your A3 is 2 by 3, 9 by 4, 4 by 7, and so on. Okay, what you should just notice here, that the AK sequence that you get, this AK sequence, the way it is 2 by 3, 2 by 3 power this and so on, the AK sequence is actually decreasing, and they will all be positive, so it's bounded below. So it's a decreasing sequence bounded below, so AK will converge to some real number C. We don't know what it is as of now. Okay, so AK will converge to some number C. Now what about BK? Okay, so it comes only when, okay, so BK, sorry, yeah. So what is BK? BK, if you notice, will come out to be 2 power k minus 1, 2k minus 1, which will be 2 minus 1 over 2k minus 1, and this, if you notice, will converge to 2. Okay, so with this you see that the sequence UK x will converge to CX square. Okay, that will be the limit of the sequence. So this is your y that you're looking for, y of x, right? By the Picard's iterative process, all these uk's were converging to y, right? C, where this y is cx square. If we find y, then we have found y. If we find c, then we have found y. Now, finding c, okay, finding c basically. So how do you find c? You use this information we have here. You have this recursive relation. Both have uk. So if you take limits here, right, both will converge to cx square. So if you the left hand side of the integral will converge to cx square, and the right hand side will converge to 2 by 3 integral 0 x uk minus 1 power half, which will converge to c square, which is square root of c s ds, which will give you 2 by 3 square root of c s square by 2 of 0 to x, which is 2 square root of 3 x square by 2 and then 0. So this is same as x square by 3, and this is cx square. Now this implies that square root of c is 1 over 3, or in other words, c is 1 over 9. So c is 1 over 9, then your yx, the solution that you obtained as a limit of the Picard's process, is actually x square by 9, in other words, x by 3 whole square. Right? Now this is also a solution to this initial value problem. So you see, already you obtained 0 as one solution. You have one more solution, which is a non-zero solution of the same problem, and this solution you obtained from a different, you also obtained it via the Picard's iterative process, but from a different choice of zero order function. Okay, and here it's here it's a non-linear problem, so it has more, in this case it has more than one solution, and here you are able to obtain different solutions by different choice of zero order approximation. So that was the purpose of this assignment, that you could obtain the other solution also from Picard's iterative process just by changing the starting point of the sequence of the Picard's iterative process. Okay, so with this I think we complete everything. I hope you will complete whatever I left here in DEC, just to in case you want to verify this D and D, so conclusion D for kth order linear, you should know that if y prime plus qxy is the first order linear homogeneous, then a kth order linear homogeneous will look like, let's say, ak yk minus 1 yk minus 1 and so on up to a 1 y prime plus a 0 y. Okay, this is your general kth order linear homogeneous equation. Okay, so whatever we have done here for first order, whatever you need to so basically if you need to check that the set of all solutions of this is a vector space, you can see that it will, because there is a linearity in y anyway. Okay, so with this we stop. We will see you in the next session. Thanks a lot. Bye.